Hi everyone, it's Mr. N, and we are going to work on the chapter 2. This is the third review that you guys got in class, so let's go ahead and take a look at this and do some of these problems. On the first question it says, sample problems. These you can use a calculator, so make sure you understand on these, it's best to have your calculator handy. For this first one, it says, if f of x is in between 1 minus x cubed and 1 minus 2x squared, then find the limit as x approaches 2 of f of x. Well, taking a look at this looks definitely like the squeeze theorem, so we're going to look up the squeeze theorem and make sure we use what we know about the squeeze theorem. And the squeeze theorem says if the limit on this side and the limit on this side converge or are the same, then f of x has to have that same limit. Or more importantly as well, if this limit has a value and that limit has a value, then we know the limit of f of x at that value will be in between them. So let's take a look. Let's put in 2 first here. We're going to try direct substitution. We'll get 1 minus 2 cubed, so this is going to be negative 7, and that's going to be less than or equal to f of x. And the limit here, so the limit again is what we're doing as x goes to 2, is going to end up being 1 minus 2 times 4, so 1 minus 8, so that's also negative 7. So that means the limit as x approaches 2 of f of x, since it's sandwiched between negative 7 and negative 7, has got to be negative 7 as well. So that's how you do this first problem. Okay, now moving on to the second question. It says find the average rate of change. Okay, right away we see this says average rate of change, so we know this has to happen. This happens over a time interval of f of x, which equals 2x minus x cubed over the interval 0 to 3. Well, since we want the average, we know that the average rate of change is the change in position, and in this case it's going to be the change in f of x over the change in time, and in this case it's just x. So normally sometimes we see it as s of t or x of t, but this time we have an x. So what does this mean? Well, this means that this is my interval from 0 to 3, so that's going to be my delta x. So that'll be 3 minus 0. My change in position here, or the delta f in this case, is going to be f of 3 minus f of 0. So let's work this out. When I go ahead and find f of 3 is going to be 2 times 3 minus 3 cubed. So now, working this out, we get over here, we're going to end up with 6 minus 3 times 3 is 9 times another 3 is 27, and this gives me negative 21. So this will be negative 21 over 3, which ends up being negative 7 as our average rate of change. Now, so what if I had asked for the instantaneous velocity, or in this case, instantaneous rate of change? So instantaneous rate of change happens at a point, so we would need a point. So suppose I asked for the instantaneous rate of change at x equals 3. Well, in this case, we need a slope. Later we will learn how to do this with a much easier format. It's going to be a two-step process really quick, but for now we need to be able to find that slope, and the way we've done it is we need a slope from point P to point Q, and in this case point P would be the point at x equals 3, so we could plug 3 in and get this value of negative 21, and the point Q would be x comma f of x. And remember how we did this? We said f of x minus the negative 21 over x minus 3, and we want the limit as x approaches 3 of that. And you would have to solve this, and that would give you the instantaneous velocity. In this case, instantaneous rate of change. So now looking at number 3, this transitions into what we had just talked about with the instantaneous rate of change. So what I need here is to write the equation of the tangent to this function at x equals 1. So I need the slope of that tangent, which is the first step. Over here, since we have the value at x equals 1, what I want to do And let's set this up with another color. What I need to do is I need to find that slope, and I have the point P, which we're going to call 1, comma, plugging the 1 in, we'll get negative 2 plus 4, which is 2. So that's my point P, and then my point Q is going to be x, comma, f of x. So now I need the slope from P to Q, and in this case we would end up saying f of x minus 2 over x minus 1. And I need the limit of that slope from P to Q as x goes to this 1 value. So, working this out, f of x becomes negative 2x squared plus 4 minus the 2 all over x minus 1. So, let's see what we can do with this. Over here, I could simplify the top to say negative 2x squared plus 2 over x minus 1. I can go ahead and factor out, let's just do it underneath here, factor out this negative 2, and I get x minus 1, x squared minus 1. And in this case, let's go ahead and clean that up just a teeny bit here. We will rewrite this as x squared minus 1 over x minus 1. And this ends up factoring to x minus 1, x plus 1 over the x minus 1. So the x minus 1's reduce out, and I'm left with negative 2 times x plus 1, which is my slope, at the point x equals 1, because I'm taking the limit of this again as x goes to 1. So the limit of this ends up being negative 2 times 1 plus 1, which is my slope, and my slope is going to be 2 times negative 2, which is negative 4. That is the slope of this tangent. So what would be the equation of the tangent? Well, we could say y minus y1. We go back to our point P here, so that would be y minus 2 equals negative 4 times x minus x1, which is 1. Again, y minus y1 equals m x minus x1. So that is our equation of our tangent line. We found the slope, we went ahead and found the normal. Well, we went ahead and found the equation. Now, I asked for the normal as well. Well, the normal is the perpendicular slope. So this perpendicular slope ends up being 1/4. And then we just write the same thing. Y minus 2 equals 1/4 x minus 1. That is the equation of the normal. All right, now moving on to problem number 4. It says, use IVT to show that this equation has at least one solution. Next, find all the real solutions. So let's go ahead and break this down into what we're going to do. And in this question, we have to use IVT. So IVT says that if a function is continuous, it will have some intermediate value, and that's the basics of it. Go ahead and review the IVT video if you need to. But let's see. What we're looking for, since we need a solution, is we need a change from positive to negative, or vice versa, from negative to positive. So let's go ahead and graph this with our graphing calculators. And when you graph it, you get a function that looks something like this. This is just a rough sketch of it, but it looks something like this. Well, look, it crosses right here. This is at negative 2 roughly, and this right here is at positive 2. Well, look, it crosses the axes 3 times. This is a positive, that's a negative down here. This is a positive, that's a negative. So it goes from negative to positive, then from positive to negative, then from negative back to positive. So this has 3 solutions. And how do I know? Because IVT says it has to be continuous. Since it is continuous, it has to have intermediate values. Well, what is in between a positive and a negative? A 0. So it has 3 solutions, so we could say 3 zeros. Now, we can go ahead and use our graphing calculator to find what these 3 zeros will be. And there are multiple ways to do this. I suggest not using the trace feature, but rather going second calculate if you're using a TI, and finding, I don't have the TI here that I could show you in this video, but you go ahead and do the steps for it. Okay, so using the graphing feature, you graph it, then second calculate, and find the zeros. the zeros should end up being at x equals negative 2.33. Another one at x equals, this will be 0.2016, 0.2016, and then your last zero should end up being at x equals 2.1284, 2.1284. So those end up being your three real zeros for this problem. Okay, now moving on to question number 5. On question number 5, it says graph f of x equals the greatest integer of x plus 1 on the interval from negative 5 to 5. So we can quickly put in a grid here. And if you do this on your calculators, just be careful where your open circles and closed circles are on this interval. So if we go from negative 1, 2, 3, 4, 5 to positive 1, 2, 3, 4, 5, remember, at 0, this will be 0 plus 1, so it'll be at a height of 1. Now, where will this be at a height of 1? If I'm at 1, or if I'm at 0.9, so the greatest integer function, 0.9, that's going to be 0, plus 1 will end up being 1. So all the way to this value right here, it'll be at 1. Well, what's the greatest integer of, if I say negative 0.9? Well, at negative 0.9, remember, we want the greatest integer at less than or equal to it, so we move to the left, so that would be negative 1 plus 1 would give me 0. So we end up with that. So here, basically, we end up with this stair-step function that goes this way and then comes down this way. So which is the open circles and which are the closed circles? Well, remember, it has to be closed on this end, which means it'll be open. This will be closed, open, and that'll be closed. Right here, this will be open because, again, it's the greatest integer less than or equal to it. So that'll be closed and open. So the left sides are closed, the right sides are open, and you can continue this all the way down to there. So basically, that's how we graph the greatest integer function. So you can use your calculators, but be careful with what you get from your calculators. Okay, now moving on to the first of the no calculator questions. Again, these are no calculator, so try to do these questions right here without using your graphing calculator or a calculator in general to help you. So on this first one, it says let f of x be 5x squared minus 2x and the point P be 1, 3. So find the slope, the equation of the tangent. So it's very similar to what we just did above. We need the slope, the equation of the tangent, and the normal of f of x at point P. So at point P, this is what we have, 1, 3, and Q, again, is going to be x comma f of x. So the first thing we have to do here is we need to find the slope from point P to point Q. And we want the limit as x approaches 1 to be able to get that slope, because we want it to happen at x equals 1. So this slope becomes f of x minus 3 over x minus 1. Again, it's the y's over the x's. So working all this out, and we want the limit as this approaches 1. So working all this out, we end up with 5x squared minus 2x minus 3 all over the x minus 1. And factoring this out, we end up here with 5x plus 3 over x minus 1. And on the bottom, we've got this x minus 1. So these reduce, and now we're able to do direct substitution for the limit. And we plug that in, and we're going to get a value of 8, which is our slope from P to Q. So since we have a slope, that's this first part, we're done. Now we need the equation of the tangent. The tangent will be y minus y1 equals mx minus x1. So y minus, again, we're using the point 1 comma 3, so we need point P, which is 1 comma 3. So this becomes 1 minus 3 equals this slope 8 over x, times x minus the 1 value. Now, the normal, that should be easy. You already have the slope, but we need a perpendicular slope for the normal. So we had a slope of 8. The perpendicular would be negative 1/8. Now I can just finish writing my equation. It'll be the same thing. Y minus 3 equals negative 1/8 x minus 1. So you use the same points as before. Okay, take a look at the next problem. Here for step A, they want us to find the limit as x approaches 2 from the left of f of x. Okay, so 2 from the left means I'm going to look at the top part of this piecewise function. I'm looking here. So 2 from the left ends up plugging it in. You'll get simply a minus 2 cubed, which is a minus 8. That's it. That's part A. For part B, 2 from the right, well, from the right, I'm approaching this right here. That would be 2 from the right. And this, again, plugging it in, you're going to get a value of 6. We could do direct substitution since that is a polynomial. For part C, it says, find all values that make f continuous. Find all values of a that make f continuous at 2. Well, for something to be continuous, remember, we have to trace it without picking up our pencils, so we cannot have a discontinuity. So these two values must equal each other at 2. So in other words, a minus x cubed must equal this 3x at x equals 2. Well, let's plug in x equals 2, and I'll get a minus 8 equals 6. A is going to be 6 plus the 8, which is 14. That is what a has to be for this function to be continuous there. All right, so now let's take a look at number 3 and number 4. On number 3, it says below is the graph of f of x, so we're taking a look at that graph. On number 4, it says below is a graph of g of x, so that's the g of x graph. Then we're asked on what intervals is f of x continuous, and then on what intervals is g of x continuous. So let's first start with the f of x equation. Now remember, we talked about continuity, and we said that continuity, you could think of it as wherever I got to pick up my pencil when I'm sketching the graph, and I got to pick up my pencil and start over, that's a point where it's discontinuous. So there's no, so in this case, we're looking at a jump discontinuity, and this one would be removable. So I would trace it, but I got to pick up my pencil, continue on the other side, and then here we have the infinite discontinuity. And again, from here, pick up my pencil, come down here, move up. Same thing with g of x. I can move up, oh, got to pick up my pencil to continue. So on the f of x one, let's take a look. We're going from negative infinity all the way to this value of negative 3. Okay, and we are going to open those because it's not included there from the left side of negative 3. We're going to union this with negative 3, but with a closed bracket because this point is included. And then we will continue all the way over here. Take a look. We will continue all the way over here to 1. So 1 and open again because we're not including that point. We will union this from 1 to this right here where the asymptote is 3, and again open. So now one more interval here. We're taking a look at this again, negative or positive 3 all the way to infinity now because we trace this and it's going to go all the way out to infinity. So those are the intervals on which f of x is continuous. So let's look at it again. So here we're going from negative infinity all the way to negative 3. We're going to union this with negative 3 to 1, from 1 to 3, and then these again are open, and these are open, and then from 3 to infinity. Now let's take a look at g of x. So taking a look at g of x, we have the same sort of situation going on here. So for this one, we're going to go from negative infinity to this asymptote here at negative 5, and those will both be open. We'll union this from negative 5. We come down all the way to negative 2, and that's included. Union that with negative 2 open because we're not going to include this all the way to 4. And that's open there because this is the removable discontinuity again. And then we've got from 4, so we'll union that from 4 to infinity. So let's look at it again, just double check our work. From negative infinity to negative 5 to negative 2, so that we're union those. Then we've got from negative 2 to, we're going out here to 4, and then from 4 to infinity. So we union these together, and that is where g of x is continuous. So now we are looking at number 5. And number 5 asks us to use these graphs to estimate these values. Let me slide this up just a bit. Okay, and let's take a look. For here we have the limit as x approaches 1 of f of x times g of x. Remember, we learned that on these limits you can break them apart and do f of x times the limit as x approaches 1 of g of x. Do them each separately, then do the multiplication. So for this first one, when we find the limit as x approaches 1 of f of x, we are taking a look at this graph right here, and there's the as x approaches 1. That limit is going to be 2. So over here, this is going to be 2 times. Now let's take a look at the g of x graph as g of x approaches 1. Right there, we're going to estimate that to be about negative 1. So we're going to come down here, and that limit will be about negative 1. Again, here for f of x, as x approaches 1, we were up at 2. And we go from the left and from the right, and they both converge to there. And here at 1, we're going to come down, and from the left and from the right, again, that's going to be an estimated value of negative 1, which gives us a value of negative 2. Part B, we want to do a division problem. On this one, again, you can break it apart and do the top as it approaches negative 1, and then the bottom as it approaches negative 1. So let's take a look at g of x as it approaches negative 1. Well, here's negative 1, and I'm down here on the graph. I'm going to estimate that to be about negative 2. So from the left and from the right, it's approaching negative 2 at when x is negative 1. So let's go ahead and write that in. So this one is negative 2. On the bottom here, we're going to take a look at the f of x graph. So we come back to the f of x graph as it approaches negative 1 from the left and right. Well, that one's tough. We can kind of say maybe that this is right here. If I go up, it's a little bit underneath 1, but since we are just to estimate, we're going to go ahead and use the value of 1. So right here, again, since we are just estimating, we're going to say that from the left and from the right at negative 1, it's just about 1. So let's go ahead and put that in. And this answer ends up being negative 2. And finally, we want the limit as x approaches 4 of x plus g of x. So this should actually be in parentheses like this. So let's just clean that up a little bit. So the limit as x approaches 4 of x, what would that be? So right here we have the limit as x approaches 4 of just an x, plus the limit as x approaches 4 of the g of x. Well, sometimes it's these easy ones that confuse us right here. That's just going to be 4. Why? Because you're just plugging in, you can do direct substitution. Remember, y equals x is a diagonal line, so at 4 it'll be 4. Over here, the limit as x approaches 4 of g of x, well, we're going to take a look at our g of x graph at 4. Look at from the left and from the right, they both approach this 1 value. So this will be plus 1, so the answer to this is 5. Okay, now moving on to number 6. Let's pull this all the way up here and take a look at what we have. It says, the table below shows several measurements of velocity of a car driving on a straight road. V of t is continuous on the interval from 2 to 20. So we know from 2 all the way to 20, this is continuous. So I can connect all these points without picking up my pencil. All these values, all these points right here, I can connect them without picking up my pencil. So what is the least number of times where v of t is exactly 350 meters per minute? All right, let's make this visual. Let's take a look at what we got. So I'm going to quickly sketch a little plot here, and I'm going to just estimate some values. So at 2, let's go ahead and let's just do a little better estimation here. We don't need it so perfect. So we're going to say this is 2, this is the point 241. Okay, so this is the point 241 and change. Okay, so over here, the next one is at 5, and we're up a little higher at 313 and change. Then we go to 8, and we're all the way up to 4. We jump really high up to 465 and change. So that's at 8. And again, I'm just estimating here. At 13, we jump all the way up to 572. And then at 17, we come all the way back down to 411 right there. And then at 20, when we get all the way out here to 20, we are below both of these at 287. So somewhere right around there. Okay, now remember, again, I am connecting these with a straight line, or not a straight line, but a curve, because it's continuous. It could go up in between here. I don't know. I don't have values, but I'm just going to guesstimate that that's what it's going to look like. Well, we want something to be 350 meters. Exactly 350 meters. Well, at 350 meters, that's right there. Okay? That's somewhere right there. So that's below this 411 value and below this 400 and above this 313 value. So right in there. Okay, and this is the 411, so I'm going to get just below that and above the 313. So I'm somewhere in here. If I would have drawn this graph a little bit better, you could see that I am somewhere in there. So what does this mean? If I connect these points, whoop, I crossed once, and I had to cross again. So if I connect all the points on this interval, I had to have crossed this value twice. So the least number of times where it's exactly 350 would be 2 times. I crossed my line twice, and this is by IVT. The intermediate value theorem says if to get from here to here, I got to cross through right there. To get from here to this point, again, from this point to this point, I got to cross through right there. So I had to cross this 350 mark twice. So at 2 times, I was at 350 miles per hour, or meters per minute in this case. So that's all IVT again. Okay, moving on to number 7. Number 7 says the function f is a continuous for -3 less than or equal to x less than or equal to 2. If f of -3 is 2 and the inverse of 6 is 2, which of the following statements must be true? Well, let's take a look at what we have here. In this case, I am taking a look at these function values. And I can quickly, again, if it helps you to make it visual and sketch a graph, let's use this color right here. Sketch a graph from -3, and then we're going all the way to 2. All right. Well, they tell me at -3 I have a value of 2 right here. F of -3 equals 2. The inverse of 6 is 2. Well, so that means f of 2 equals 6. So at 2, I'm up at 1, 2, 3, 4, 5, 6. I'm way up here. All right. So there exists a c that f of c is 1. Where would f of c be 1? F of c would be 1 right there. In order for me to go from this point to that point, do I have to cross that 1? No, I don't. So that doesn't work. So we can undo those and say, okay, well, that one doesn't have to be valid. Okay, so now this does not work. Look at the next one. There exists c such that f of c is 3. All right, well, over here I'm at a height of 2. Over here, I'm at a height of 6. So 1, 2, 3 would be right there. Does that work? Is there a C such that f of C is 3? Yeah, there has to be. Yes, absolutely. Look at the next one. Is there one where it has to be -1? No, to connect from here to here, I don't have to go through -1. So that one doesn't work either. And has at least 1, 0? No, when I'm going from -3 to 2, these points right here, I don't have to cross through 0. And the limit as x approaches 2 exists. Well, here's 2. Well, the limit 2 from the right exists, or I'm sorry, 2 from the left exists, but 2 from the right doesn't. So if I'm coming in this way, I don't know what's happening up over here. Here, it does exist from the left. So since the left and right do not converge, we cannot say that this one exists. So the only possible choice here would be B. And finally, again, this is an IVT problem. The function g is continuous on the closed interval from -2 to 3. Some values of g are shown in the table. So there's x and there's g of x. The equation g of x equals 1 must have at least 2 solutions on the interval if k equals, well, let's take a look. Again, let's try to make this a little bit more visual. So I am going to plot some points here. So at -2, I'm at 1, 2, 3, 4, -5. At 0, I'm at 6, 7, -8 down here. At 1, I'm at some k value. I don't know where this k value is. Somewhere along here is a k value. I'm going to just dash this line. And then at 3, I'm at -4. 1, 2, 3. I'm at 1, 2, 3, -4. Right there. Well, I'm looking for 2 solutions if g of x is 1. So g of x being 1 would be right there. So that is g of x being 1. So that means I got to cross through that line twice. So where am I? I could have changed this interval. I didn't have to say from -2 to 3. We could have said from -1 to 3. It doesn't matter. But we're looking at this whole interval, so that means I can connect the point here, and I need to place k. If I place k down here, does that mean I have to... So again, let's take a look. If I place the k down here, does that mean I have to cross that top red line to connect these points? No. If I place k right here? No. What if I place k right on the line? Well, then it would only touch the line once. It won't go through that line twice. What if I placed k up above, higher than 1? Yes. If I placed the point k somewhere way up here, then for me to connect all these dots, I would have to cross through this red line right there twice. Right here and right there. So that means we have to be bigger than this. We have to be bigger than this one value. So the only possible choice that is bigger than is E. So if I put this up at 2, then I will be crossing here twice, and that's what we were looking for, at least 2 solutions. So thanks for watching, and good luck on the test.